The best way to use this video is to watch and pause at certain points and see if you can answer the question yourself. The video is very similar to how we work problems in class. I will lead you to a point and then I'll ask you to think about what comes next. Please pause the video and do that good thinking. It will speed up your mastery of the material. If you come back from having decided on what you think the answer is and play the video again and it turns out you got it right, fabulous, proceed. If you did not get it correct, then I would ask, go ahead and watch the rest of the video, but make a note of it and follow up with me or your lab instructor or your tutor, because questions like this can really help us to learn and master physics faster. It could be your idea was a completely fabulous one that was just another way to solve the problem. Recall, many of the problems that we work will have more than one correct route or answer. Or it could be that you have a concept or equation misunderstanding, and that's learning. And if we can sort it out, then the next time you encounter it, you'll get it right. Okay, I'm going to start by labeling all of the capacitors with letters. The letters that I'm giving don't really have anything to do with those other letters that you see in the diagram. Those are just showing junctions or locations in the circuit. I'm labeling the capacitors to make solving the problem a little bit easier. Next, I'm going to read the problem and figure out what information they're giving me and what they're looking for. So this has two parts to it. They give me that the potential difference across the 1 microfarad capacitor is 10 volts. That's the one that I've labeled A. So I'm going to write down V, potential difference of A, is 10 volts. All right, and for the first part of this problem, we want the equivalent capacitance of the entire network. That's between the letters A and B. Now, not the ones that I just wrote on the document, but the ones that were on there originally. So that would be the equivalent capacitance of all of those capacitors combined. For the second part of this problem, it asks for me to calculate the potential difference between C and D. So again, those letters C and D are the original ones that were on the document. So the potential difference between C and D would be the potential difference on the 3 microfarad capacitor, or the one that I've labeled D. Pause the video and think about how you would break down this network. The first thing that I'm going to do is bring that 2 microfarad capacitor that's labeled C around the corner that's above it. Recall, I can do that if there are just 2 lines meeting, but not if there are 3 lines meeting. So I couldn't move that 3 microfarad one around a corner, or the 7, but the 2 I can because there are only 2 lines meeting there. All right, my first step is that A, B, and C are all in series. Our next step is identifying that the capacitor labeled ABC is in parallel with D. Let's resketch again. This time we'll replace the capacitor labeled ABC and the capacitor labeled D with a single capacitor labeled ABCD. Looking at this sketch, we can recognize that our very last step is going to be that those 2 capacitors are in series with each other. Pause the video and use the roadmap that we just laid out to try to calculate the equivalent capacitance on your own. All right, let's go back and look at our roadmap. A, B, and C were in series. My capacitor combining rules say that if I want to combine capacitors that are in series, they add as 1 over. So 1 over CA plus 1 over CB plus 1 over C equals 1 over the equivalent capacitance of CABC. All right, next up. Those were in parallel. So we're going to go use our parallel rule. For parallel capacitors, they add just directly, and that will give us the equivalent capacitance if we were to remove ABC and D and replace it with one equivalent. Final step. Those were in series, so they will add as 1 over, and that gives us our equivalent capacitance for the entire network. The second part of this problem is asking for the potential difference across the capacitor, which I labeled D. We're going to use the equation charge equals capacitance times potential difference. Recall, I can use that equation as many times as I want as long as I put the same subscripts on all terms. We know the capacitance on D. That was part of what we were given in the beginning. If I knew the charge on D, then I could use this equation to solve for the potential difference on D. Let's go grab our very first picture. And the reason I'm picking that one is because we were given some information about A. We were told the potential difference across A was 10 volts. Since A, B, and C are in series with each other, their charges are equal. I can use that equation again. Q equals C times V. Only this time, I'm going to use subscripts of A on every term. And I'm going to use that to calculate the charge on A. Since those are all in series, the charge on A equals the charge on B equals the charge on Z equals the charge on that whole branch, Q, A, B, C. I'm going to use Q equals C times V again, only this time with subscripts of A, B, C. All right, and I'm going to use that equation to solve for the potential difference across the combined ABC. So I'll use the charge that I just calculated, the capacitance, which I calculated earlier, to get the potential difference across ABC. All right, now I'm going to grab my picture from when I had the combination of D with ABC and look at what the situation was. They were in parallel with each other. Looking at my rules for capacitors and what is the same when they are in parallel, I see that it's the potential difference. That means the potential difference of each branch equals each other, and it equals the potential difference of the whole thing combined. So the potential difference on the 3 microfarad capacitor is 20 volts.